Hi. So, I'm Byren from Adran. so, official title systems consultant. I like to call myself a photon routing expert or a wavelength wizard, depending on what you want to hear the day. And so, my talk today is just to show everybody or demystify WDM. Because there's a lot of you guys that have networks in the field. I think this picture is pretty much normal to everybody. You've got your access technologies there, be it PON, business, Ethernet services, and you're aggregating these services onto dark fiber networks, which then eventually get aggregated onto metro networks, be it your own network or carriers or whoever. So what we're seeing happening currently is all these aggregations are happening on grey fiber networks or grey optics on dark fiber networks. So this becomes like a next top type of network architecture. You've got dark fiber, you're probably running 10G on it. I think most people in the room are running 10G at the moment. And or 100G services. So the idea here is this fiber is underutilized. It's not what fiber was meant to be. And I understand for most of the IP guys, fiber transmission seem to be a bit of a dark horse, black box, whatever weird magic happens in there. And that's where I think me and the three other colleagues here today from Flex Optics and Smart Optics are trying to demystify and show you guys it's actually very simple. So what happens in these typical environments, like I said, it's dedicated dark fibers, nothing funny. It's one channel, and you're probably paying anything for a ring like this or a 3-node ring like this, you're probably paying 160,000 rands for the fiber over a 6-year course, right? The problem that happens is upgradability is an issue. Either you have to swap the boxes, buy a new fiber, like in this case where this operator had to upgrade to 20 gigs or an additional 10 gigs, so they had to buy another set of grey plugs and another fiber. So there's another 160,000 rand sunk across 6 years. So also shared bandwidth, you can't do anything with that layer. So what I'm here to show you guys is the wonderful world of WDM. So we talk about the battle of the bands. WDM has multiple bands that we can work within. So we have what we call O-band. It's a very low cost-efficient service. It's built for 5G RANs, typically for 5G frontal. Because it's so cost-effective, the big issue is it has very limited reach. You cannot amplify these networks. They run up until 10 kilometers and that's it. Your scaling, you can only run 16 channels on this, and I'll tell you in a moment why channel count is very important. Then we get CWDM, so early days of wavelength division multiplexing, CWDM was the king. It's easy to set up, optics are cheap, built for access and aggregation networks. However, yet again, only direct detect optics, nothing funny. Low scaling up to 60 channels, and you cannot amplify these networks. So they're not built for the typical African market where fiber is not good. And I think a lot of you guys that have fiber have the issue of quality, especially in the metros. Then you get DWDM, dense wavelength division multiplexing. This is the cream of the crop. This is where everything's going at the moment. I mean, we're building optics that plug into routers that go straight into WDM networks. These scales to the full C-band, so you're sitting with 4.8 terahertz worth of spectrum. You can do multi-domain networks. This can be access, core aggregation, national long-haul undersea cables, all that. You can run coherent optics on there, so 100 gig wavelengths, or currently we're running up until 800 gig wavelengths on systems. And the downfall on it is it requires some very precise management, right? So you need like GMPLS control plane, or as some of the vendors will call it, ASON. and it requires some technical skill set to operate and manage. And I think that portion is what scares a lot of people away from WDM. So what do we do? So I'm going to focus a bit today on WDM as a whole. O-band and CWDM are conversations in their own rights, but I think most of my colleagues will agree that WDM is the primary driver in transmission communications at the moment. So you've got 3 possible scenarios that you can run, and at the edge, it depends on the type of routing you're doing, the ease of use to customer and all that. So you've got what you have, dark fiber, and Matthias will actually touch on that today or right after this, where you've got a dark fiber like you would run your original setup, but you put colored optics on it. So you've got like a 100 gig ZR or a 400 gig ZR plug that's plugged straight into your router, and that is the simplest. It's a day one solution, but you already have the base for WDM. It's a colored optic, so you can run within the spectrum. Yet again, it's just 1 fiber pair per service, and complexity in managing numerous links. So if you've got multiple links, that's how it's going to work. Then we get what we call fixed optical add-drop multiplexers. So these are passive WDM filters. I run 1 fiber pair on it, but you can run up into 80 channels. So that is already 8 terabits worth of traffic on a single fiber pair that you've purchased. Low capex, very easy to set up. No active equipment. The only active equipment is the chassis you manage. You've got fixed wavelength grids, so it's fixed slots of either 50 gigahertz or 100 gigahertz, or in some cases 37.5 gigahertz. And you've got a fixed traffic matrix, so you've kind of got something static. You physically plug in these cables onto the filters or muxes, and it is what it is until someone goes there and changes cables around. Then we've got what we call ROADM-based, so reconfigurable optical add-drop multiplexing. So these are components that have, we call them WSSs. The most simplest explanation of it is it's a little silicone mirror in there. We pull some energy through it, and it changes its angular, it's an angular mirror, and it drops a specific frequency or picks up a specific frequency and routes it. So it's a photon routing piece of equipment, so it routes photon. Where you guys route IP addresses, we route photons. It's flexible, reconfigurable. You can sit in a NOC, create services. You just need someone to plug in the transponder or patch lead on the other side, and it runs. It's built for any baud rate, so you can run anything from 100 gig service per wavelength up into a 800 gig wavelength service. So 800 gig per wavelength on a 4 terahertz network, you can run up into 25 terabit on a single piece of fiber. So that's nice. And it's expensive. it's what it is. And I think when we go through this journey, everybody's going to at some point ask you, what's the cost? And we'll get there, and let's hope it's not as shocking to you guys as it is to most of our customers. So the idea is, in Access WDM, we have 2 models, like I already said. You've got, at the top, you've got what we call a mux ponder. So you take a layer 2 device. This is currently how it was done for many years. You take a layer 2 device, you take a grey optic, an LR4 optic or something like that, plug it into what we call a mux ponder. This mux ponder takes multiple 10 gigs, 32 gig fiber channel, 16 gig fiber channel, 40 gig E, and all these things, and puts it into a single wavelength as 100 gig, and you transmit your services like this. So it's an active piece of equipment. It is completely transparent. It does not look into any of the active IP headers. We just take IP information and we pack it into an OTM frame and we run it along in a RAID. The new school of thought and the new technologies that we're seeing is we're removing that mux ponder layer, which is a high cost layer. So a typical mux ponder layer, you're looking at anything between $12,000 to $20,000, depending on the mux ponder, on 100 gig. We're removing that layer and replacing it with an optical layer, which runs anything between $3,500 to to $4,000, also depending on the optic itself. And so we're immediately now cutting a cost layer in the access layer that was not there. So we're making it more accessible to the IP guys to start running transmission networks. So basically how that architecture will look is you've got your single fiber connected to the network. You're now running possible line capacity of anything from, so you can run 10G or 100G optics, and you can run any line capacity suddenly from 80 gigs up until 4 terabit line capacity on a simple system. Your optics can either be fixed or tunable 10 gig WDM direct detect optics. This could be 100 gig coherent WDM, 100 gig ZR or 400 gig ZR. And your distance ranges now suddenly become up to 120 kilometers, in many cases unamplified if the fiber is good. Your client traffic add drop is layer 2, layer 3, which I think everybody in the room is comfortable with, nothing funny there. And your line traffic is layer 1, so pure OTN photonic routing. Your traffic protection is done at layer 2 or layer 3, so your typical Ethernet ring protection, if you ERP if you want to do that, or whatever other technologies you use. So from the technology is you can take into your OLTs, sorry, stop doing this. You can take into your OLTs or customer CPEs or routers, you plug in these 100 gig optics or 400 gig optics, plug it into what we call a line filter or a MUX. So there's all those little colored blocks there by the routers. I think this does have a laser. So you plug it into those little filters that we call MUXes, and you now can route your traffic next neighbor as much as you want to. Upgrading traffic is simple. If you've got a node, like that node that is a 10G node, but the past traffic on it has to upgrade to 100 gig nodes, but there's no considerable value in upgrading that node, that switch to now accommodate 100 gigs or something like that, you just upgrade the nodes that require it, and you can do pass-through traffic. So it's quite simple in that case where you can do that. You can ring protect this, so you can create proper rings that are closed. It doesn't just need to be a string network or a ladder, or I think there are many terms for that. And your capacity, you can run up to 40 times 10G, 100G. You've got shared backbone bandwidth, so if you've got a customer that suddenly wants to bring down their own kit onto the network, you just give him a colored optic, put his kit next to yours on the filter, and it goes along. Then what makes WDM a bit more better is you can do add drop and bypass. So it's not just typical next neighbor traffic where you have to go optical, electrical, optical again. You can bypass a node completely. So in this case, OLT at node 1, we bypass, and we take the traffic from node 2 to node 3 directly. So in a lot of cases, as your bandwidth demands grow, you want to hand off your traffic as quickly as possible, right? Latency is a bit of a killer, and everybody wants high-speed, low-latency networks, and optics does this for you. A typical optical WDM network will add, I think, Matthias could keep me honest here, I think in a typical WDM network, you should not see anything above 50 microseconds up to a millisecond of traffic. And this is optical to electrical conversion again. It gives you the same capabilities. You've got long-range communications. You can now bypass traffic, and it goes like that. So you're saving on fiber resources. Your cost is significantly lower when you start bringing on new services. It's a pay-as-you-grow model. So you can start with 1 channel, go up to 40 channels. In some cases, you'll hear today someone probably talk about FlexGrid, which is like super carrier, DCI, Terra capacity type stuff. And then your extra cost is just passive components and some power in nodes to manage those components. So that is the access layer. And the idea there is to really have something that is robust and small. So now the conversation starts is, what does this cost me? So if you're looking at currently 100 gig optics, if you're looking at buying an ER4 optic that reaches 40 kilometers, I think the fiberstore.com price, you're looking at about $4,000. If you're looking at ZR optics, QSFP 2800 gig ZR optics, you're looking at probably $3,500 to $3,800. Sounds a lot, but now you suddenly have a colored optic that you can tune to a specific frequency on anyone's WDM network, and you can do up until 120 kilometers unamplified, where the 40 kilometer optic is a bit more expensive, and it's a great piece of kit. So now we've demystified, hopefully, the access side, and I'm just going to quickly touch on metro aggregation, because I think also that is something that needs to be spoken about. Is in the metros, what we're seeing is people building distributed routing infrastructure, right? So you've got your access networks, you aggregate the traffic there, put it onto a metro network where you're doing routing decisions again, and you're distributing this across your entire metro ring. So the idea is, like I said, is to have low latency, high capacity networks. So the benefit of WDM optics on these routers is you can take these optics now that you aggregate in your access network, and you can plug them onto high capacity mux ponders that take 100 gig and put it into an 800 gig channel. And you now get rid of an additional routing layer, and you just route your traffic optically directly to the core and break out in your core ISP nodes or your core routers, your MXs or whatever you guys are using at the moment, the Aristas. And then you've got the nice little end-to-end aggregation network that has the ability to expand from 10 gig up to 200 gig, 400 gig.
Currently, we use a lot of 10 gig optics in our passive DWDM.
Yeah.
But we're hitting constraints where, I mean, we've got, I think the biggest one we've got, I think, is 12 channels. And the constraint for us is literally switch ports. It's the switches we're plugging into, we're running out of ports. And so we have 100 gig ports on our equipment, but we're struggling to find good information on what optics we can do there without having to go the active route. So we go the active route in certain places, but obviously that's quite a big investment and a big amount of infrastructure and all the rest of it. Where in some places we literally just could swap an optic using the existing muxes and move on. Can you give us an indication of where we're at in terms of passive, either at 25 gig or at 100 gig? What sort of distances? What are the options there?
So what we are seeing in the market is it's either directly take like 10 gig type of optics like you have at the moment, or we're seeing a big uptake in coherent traffic. So the idea of that is the colored optics have no range limit, theoretically, right? You can take a 400 gig ZR, and if the fiber is of good quality, you can transmit that at 200 gigs up until 1,000 kilometers with free amplification. In a typical metro access network, 100 gig coherent optics like the QSFPs, 100 gigs QSFP 28 or QSFP DDs will work in that space. The problem with 25 gig optics is there are no colored 25 gig optics. They're pretty much just gray optics. So the idea is, and also your cost is high because it's a weird rate. So for coherent, it's a good idea, especially if you've got QSFP 28 interfaces on your devices. Go coherent, and you can run and bypass traffic easily like that.
So you're saying that there are 100 gig one-wave coherent optics available in QSFP format now?
Yeah. Okay. So there are commercially available, should be, most vendors are coming out of it Q2 this year. I know a bunch of beta versions have shipped and people are busy testing it. So the big challenge at the moment with those is managing the plug, right? So I think Meintjes will touch on that after this, he'll touch on that a bit more. But QSFP 100 gigs are available.
Okay, so it's stuff that's kind of coming out of the factory now. It's not something that I should have expected to see in the market last year or anything.
No. It's coming out of the factory. It's brand spanking new.
Okay, cool.
Hi, my name's Andy Rabagliati. I'm a long-term member of the Internet Society. Yeah. I'm curious about your silicon mirror switch thing. Okay. How fast does it switch?
So The limitation is not on the WSS wavelength, so it's called a WSS, so it's a wavelength selection switch. So it switches in nanoseconds. The challenge you sit with is if you've got a network with multiple legs on it. For argument's sake, you've got a national long-haul network that touches every metro and every national backbone, the NLDs, or some of the CCOM or fiber cables. Then what happens is your control backplane has to talk to each one of these nodes to figure out what wavelength is getting dropped where, what is the capacity, what's the grid size of it, and all that. So the switch itself happens in nanoseconds. The intelligence takes a bit of an unintelligent amount of time to figure out what's going on.
Hi there, Enrico, Coherence Technology Solutions. Could you just touch on temperature limitations of the various different optics that you mentioned? So the 100 gig coherent, the
So good question, right?
Yeah.
And I know why you're probably asking this because you probably have some street cake. Oh, sorry, apologies.
No, you want to repeat it.
No, he's asking the question.
Yes, I asked.
Yeah.
No,
So,
I couldn't make out your question.
oh,
That's
sorry.
why
Sorry, just repeat that.
I was saying, could you touch on temperature limitations for the various different optical modules that are available in the market at the moment?
Yes. So I know why you ask this because you probably have a lot of street cabinet-based things where cooling is a challenge. So
Well, even in Terraco,
Yeah.
data centers, cooling is an issue.
So kit with typical WDM providers at the moment is anything from negative 40 degrees Celsius to 65 degrees positive. So you can run in these environments. Plugs typically range in the range of E-temp and I-temp, so industrial temperature. So this is uncooled DC or storage room, and E-temp for street cabinet capacities where you run that. The difference in the capacity is basically the heat sinks on the plugs, right? So if you've got for argument's sake, a QSFP28 that sits in an environment that is a 6-watt power draw, that doesn't get hot. The photonic side gets hot, but other than that, we can run, or most operators or vendors, sorry, can run 65 degrees Celsius.
And the 100G coherent optics, are they more or less temperature sensitive than the standard
So
100G optics?
they're not temperature sensitive, but they are built to handle at those E-temp environments.
Thank you.
Awesome.
Great. Thank you very much, Byren.
Thanks.
Next up is Matthias from Smart Optics.